Okay. So, yeah, thanks for the invitation to talk today. And really, what I'm presenting today is, in a lot of ways, is a talk about data. Statisticians are very familiar with data, but you know, a question of what actually goes into the headline global temperature numbers that we see. You've probably heard quite a lot of talk about things like the Paris Agreement target of keeping warming as close as possible to 1.5 degrees above the pre-industrial level, and how close we might be to getting there. But you probably haven't thought too much about what all the data are that underlie this. And in this talk, I'll present what's involved, some of the issues involved, both on land and at sea, and how that's all integrated into an assessment of changing global temperatures. Um, Okay, so we start here with, and this is one of the headline figures from the Intergovernmental Panel on Climate Change Sixth Assessment Report. And the key statement in the report on observed global temperatures was that global temperatures increased by 1.09 degrees, with an uncertainty expressed from 1859 to 1900 to 2011 to 2020. 1850 to 1900 here is being used as the best available indicator of pre-industrial period. It's not true pre-industrial, of course, but it's the earliest period from which we have observations covering a reasonable period of the globe. Since the IPCC report came out, incidentally, it's continued warming, and 2023 was particularly warm. So if we take the warming to the most recent decade, 2014 to 23, the number goes up to 1.19. Now, this is combining air temperatures over land with sea surface temperatures. Our land warms faster than the ocean, so over the time span we assessed in the IPCC report, land warmed by 1.59 degrees and the oceans by 0.88 of a degree. Now, one question which might get asked here is, okay, why do we use sea surface temperatures rather than air temperatures over the ocean? And that's largely about available data, and I'll talk a bit more to later on about some of the sources of sea surface temperature data. So let's start with how observations are made, and beginning with land. And temperature observations are made at weather stations. There many of these worldwide. Got an example here of one in the Western Australian outback. Australia has I think about 700 sites that measure temperature, of which we use 112 in our long-term data set, which I'll talk about in a little bit more detail later on. And globally, when you look at all the countries in the world, there are tens of thousands of sites up there. Now, in terms of how long data are available for, we have observations in Europe which were back well into the 18th century, even a few fragmented ones into the 17th. But on the other side of the coin, Antarctica has very little before 1957-58, when a big network of stations was set up under the auspices of the International Geophysical Year, and a lot of that has been in place until the present day. Now, how we calculate mean daily temperature, and from that mean monthly temperature and annual temperature in Australia, and in fact in most former British colonies, we use the average of the daily maximum and daily minimum temperature. That isn't a perfect match to the average, say, of 24-hourly observations, but it correlates very well with it. And because whilst now, with most of our network being automated, we can do 24-hourly observations. Historically, our stations were manual, and many of them only did observations, maybe once or twice a day. So you couldn't practically extend, even if you tried to produce an average based on hourly temperatures now, you couldn't extend it back far into the past and would run into long-term consistency issues, which again I'll speak to a little bit more. Some other countries do use different methods for calculating daily mean temperatures. At sea, historically, the obvious platform for measuring sea surface temperature observations was through ships. But the methods used for that have changed over time. Historically, the method used was normally for pretty low tech one of just sticking a bucket over the side, lifting it up onto the deck and measuring its temperature. But over time, that changed to having sensors in engine room intakes or sensors mounted on ship hulls. Increasingly, we're also seeing a lot of temperature observations made using buoys, either moored buoys or drifting buoys, and those have made a quite dramatic difference to data coverage, as I'm showing one of my later slides. We don't use satellite data for the surface temperature assessment in IPCC either on land or at sea. It does get used quite a bit for operational monitoring of sea surface temperature, and that's largely about duration of record and data consistency. As most of the satellite data sets at best go back into the late 1970s. We do use satellite data quite extensively when we're assessing temperature changes in the upper atmosphere, but that's outside the scope of this presentation. Now, when we start looking at individual stations, sometimes the raw data doesn't quite tell us what's going on. So this is one example here I've got, which is one of our long-term sites, which is Amberley, which is Air Force Base near Ipswich on the western edge of Brisbane. And this is annual average minimum temperature at Amberley, and at first glance it looks like it's not actually changing very much at all. But when we look a bit more closely, what we see here is that the Amberley site moved in 1980, and what we can see if we compare with Gatton, which is a nearby site a little bit further inland, is that before the site moved in 1980, Amberley was pretty consistently, for minimum temperature, about 0.6 to 0.8 of a degree warmer than Gatton. And after the move, it was pretty consistently 0.6 to 0.8 of a degree cooler. Now, that indicates that the site move at Amberley had quite a substantial cooling impact, probably in the order of 1.5 degrees. Now, that's quite a big impact for a single site move, but there certainly are other impacts in both directions like that, and it's something we need to take account of if we are assessing long-term data sets for climate change purposes. And now these non-climatic impacts we refer to in climate science as inhomogeneities. Can also refer to them as biases and bias correction if you look at it that way. And there's a number of causes you can have for them. An obvious one is when sites move, and one needs to remember here that we're drawing on historical data that was used primarily for weather forecasting purposes. And it's only really in the last 30 years that assessing climate change has been much of a consideration in observation networks. So, often sites might be moved because they, at Amberley, I think it better suited the Air Force's operations. Elsewhere it might happen, for example, because a site was where observations being made was being developed, or maybe it was a manual site and the observer quit or died and they needed to find someone else. It could be any number of reasons. But you also get other influences. Changes in equipment can be an issue, not so much in Australia at present, but certainly historically that was the case. And I'll speak to some examples of large-scale instrument changes a little bit later. But a large one, which I'll group in the category changes in the local site environment, Now, the one which often gets talked about here is urbanisation, because urban areas, all other things being equal, tend to be warmer, particularly at night, than non-urban areas. Uh, and that's particularly driven by having buildings and paved surfaces in close proximity to the observations. Uh, and one interesting example actually is that when we looked at the record from Observatory Hill in Sydney, which is pretty well right in the Sydney CBD, we actually found no evidence of an abnormal trend from urbanisation in the post-1910 record, which implies that whatever urban signal there was in that, if there is in that data, was already fully developed by 1910, which actually makes sense because it's a part of Sydney that's been built up since well back in the 19th century. So there hasn't actually been that much change in the local land surface properties around there. It's not close, or not close to any busy roads, at least on the same level. There's a freeway and you'd be cutting below it, but nothing on the surface. Whereas the old Melbourne site, which was right next to two main roads, you can really see the temperatures ramp up as motor traffic increases after the Second World War. But things like vegetation can have an influence as well. I've got an example of that coming up. But you can also have things like if the observing time changes. Now, you might think for a daily maximum or minimum temperature, what doesn't matter what time the observations are made, you're measuring for a day. But what you can find is that, one example which you're probably reasonably familiar with is, in a lot of southern Australia, often if you get a really hot night in summer, it's the last night before the cool change comes through. Now, our standard observation day is 9 a.m. to 9 a.m. But in the past, some sites used midnight to midnight. And if you use a midnight to midnight day, what's probably going to happen is that cool change has gone through by midnight and the minimum temperature is actually the temperature at midnight or close to it the following night, and you lose that very hot night from the record. So, that's one way where observation times can make a difference. Now, look, quite a lot of all of this is pretty well documented, but quite a lot of it isn't, especially as you go further back in time. Some things are better documented than others. So, often things to do with instruments are pretty well documented, but local site environment sometimes a bit less so. One thing I've certainly found, trawling documents over the years, and a lot of this is in, still in hard copy paper documents, particularly before the 1990s, is that public servants are very good at generating lots of paperwork when it comes to spending even trivial amounts of public money. And one particular case I remember was I was investigating a suspected site move at Launceston Airport in 1969, and I had documents which showed that the site was in one position before then and one position and another position after then. I couldn't find a document which said exactly what date the site move happened on, but what I did find was the travel expenses paperwork for the techs who were sent to do the installation. Enabled me to pinpoint the date to within a couple of days. I suspect that they weren't expecting that their travel expenses paperwork would be used for science purposes 50 years later. Now, when one of the ways we detect inhomogeneities, if there's not documentation, is by comparing with, other sites in the region, as in the Gatton Amberley example I showed before. But sometimes what you can do is when you detect a large breakpoint in a data set, you can go back into the station documentation and see what was going on. So this is one example here, which is Victoria River Downs in the Northern Territory. And what we saw here from statistical testing was we saw in 2007 there was a shift of upwards of about 1 degree in maximum temperatures during the dry season, but not much during the wet season. And going back into the station photos, we can see that the grass around the observation site was watered up until 2007, but after 2007 it was no longer watered, so you had quite significant change in land surface during the dry season. Of course, during the wet season, it's naturally green anyway, so you don't have much of a change during the wet season. Now, Australia's long-term temperature data set I mentioned before has got 112 stations in it. 61 of those go back to 1910 or earlier, and the others come in more recently. And the spread is relatively even over Australia, but there are some significant data gaps still in, particularly in the interior of Western Australia and northwest South Australia. But it's a reasonable coverage. The reason for there are two main reasons for the 1910 start date. One is that the Bureau was formed as a federal organisation in 1908. Before then, each state, or as it was before Federation colony, had its own agency responsible for meteorology. Often that was an offshoot of another government department. And they all had different standards for things like instrument shelters, and it wasn't really until after 1908 that you had national standardisation there. Also, before the 1900s, there was not a lot of data outside the southeast quarter of the country, and in particular, before about 1890, the only data in the Northern Territory or Western Australia was Darwin, Alice Springs and Perth, so very limited observations. And as well as being the data set we use for national monitoring purposes, this feeds into the global data sets I'll speak to a bit later on. Now, a few of you will probably know that one of my long-term objectives is to visit all 112 locations. I have only 3 to go, so I should hopefully knock that off in the not too distant future. So this is me at Tarcoola in the South Australian outback. You can probably tell that the photo was taken quite a few years ago. And this is one example of an observation site. Now, I've talked quite a bit about site-specific homogeneity issues, but at the global scale, they tend to cancel out. They're much more important at regional scale. But some of the big issues that we have, in assessing global temperature change are what are the large-scale systematic issues that applied in over large parts of the world. And some of the big ones there are, one is, I've already mentioned, the standardisation of instrument shelters, which in most parts of the world happened over the late 19th and early 20th century. A lot of earlier instrument shelters were not adequately shielded from the sun. So that does mean that, if you look at raw data from the 19th century, you can quite often see, very high numbers that aren't really credible. One really interesting study which was done here was actually at the Old Adelaide Observatory. And this was set up under the auspices of Charles Todd, which, in addition to his work leading the projects like the Overland Telegraph, meteorological observations also fell under his responsibility. And here they set up observations in three different types of instrument shelters. One, what we call the Stephenson screen, the square louvered box on the left, which is what we use today. A very elaborate thermometer house, which ended up not getting used much at all, probably because it was pretty impractical in most places. And what we refer to as a glacier stand, which is shaded from above but not underneath, and was the most common pre-1900 instrument. And and there's actually about 60 years of parallel observations between the glacier stand and the Stephenson screen at the Adelaide Observatory. Is by far the longest set of parallel observations of its type in the world, and that's enabled us to do a pretty good job of reconstructing the Adelaide temperature record back into the mid-19th century. A second more recent issue is a transition to automatic weather stations. Now, from manual thermometers. Now, it's not so much the transition of the actual sensors or instruments that is the issue, but often many countries used a different type of instrument shells when they moved to automated stations. We didn't. We kept the same screen design. Uh, so not so much of an issue in Australia, at least to date. Uh, it's also, as I said, urbanisation and what I'll call reverse urbanisation, and I'll explain what that is in a couple of slides' time. I did mention, for example, that the Central Sydney site was one where you didn't get an anomalous trend from urbanisation, but where you do get anomalous trends from urbanisation is where, for example, a growing city swallows up a site that was previously outside the city boundaries, and we see that a bit at a few of the outer suburban sites in Australia, but it's much more of an issue in very rapidly urbanising places such as China. But probably the biggest, if lowest profile issue of all is the changes over time in observing methods for sea surface temperature, which I mentioned. And the major one there is that the old style of doing it, which was to haul a bucket of water onto the deck of a ship, that bucket often gets quite significant evaporative cooling in the process of being lifted onto the deck. And the result of that is that bucket measurements are systematically a few tenths of a degree cooler than, say, engine room intake temperatures. And because a lot of ship fleets changed over their methods at much the same time, that if not corrected for, that introduces quite a substantial systematic bias into sea surface temperature records. And more recently, the transition from ship observations to buoys has a not as large an effect, but still a noticeable one in the order of 0.1 of a degree, which on global scale is pretty meaningful. Now, in Australia, the homogenised data actually shows more warming than the raw data, and this could be seen here. The blue line is for homogenised data set, the brown, the orange line is for raw data. These are all expressed as the difference from the 1961 to 90 average, which is why they align pretty well in that period. But the big shifts between the two are prior to the 1950s and then after the 1990s. Now, the main explanation for that is that the Australian network has actually become substantially less urbanised over time. Historically, a lot of the Australian network was built around post offices, which usually in the middle of towns, and even in quite small towns, often the post office environments will be quite built up. There'll be lots of buildings nearby. There'll often be paved streets or car parks nearby or the like. So what that means is that all other things being equal, even in fairly small towns, sites out of town tend to be cooler than in town. Now, we had two major waves of site moves out of town. The first was around the time of the Second World War, when a lot of observing sites were set up at airports, which were being used for Air Force work during the war, and most of those sites continued post-war. And then the second was when we started automating our sites in a big way in the 1990s. Generally speaking, the new automated sites were put at airports or similar locations, and the remaining town sites, many of them stopped operating. Another factor there, incidentally, was that Australia Post was corporatised around that time, and whereas before then Australia Post were doing observations for the Bureau for free, after then they wanted money for it, and that shaped some of the decision making as well. So all in all, what that means at global scale is that the process of homogenisation, or bias adjustment, on land it tends to increase the observed warming trend, but at sea it tends to decrease it. And at global scale, those cancel to some extent. Another big difference it does make is that you get much more coherent regional signals. So this is showing minimum temperature trends from 1950 on the left in the raw data and on the right in the homogenised data. And you can see here that whilst the general patterns are pretty similar, there are some fairly big local differences. For example, you can see in the raw data, you can see an area of, local pooling in South Australian Riverland, which in fact is largely driven by a site move at Renmark. And you get a lot of patchiness in the trends in the raw data, but when you account for things like site moves, you get a much more spatially coherent picture with, in the case of minimum temperatures for stronger forming, mostly in the eastern half of the country and in the tropics and subtropics. Now, sea surface temperature measurements do have their own challenges. I've already spoken quite a bit to the changes in technology, but there's also issues with data coverage. Some areas are much better covered than others, and particularly before the coming of buoys, which could deploy anywhere. The sea surface temperature observations were largely dictated by where shipping went. And this is quite nicely illustrated by the next graph. And this is showing sea surface temperature coverage over time. And there's clearly been an improvement over time from the 1890s on the top left to the 2000s on the bottom right. But you can also see some fairly interesting geographic changes. So if we look, for example, at the 1890s, you can see plenty of traditional shipping routes. You can see the routes from the Red Sea towards India, Singapore, or down to Fremantle. You can see routes routes in the Atlantic. You can see Southern Ocean routes around the Cape of Good Hope or Cape Horn. And one interesting thing here to note is there's quite a marked shipping route from the west coast of North America down around Cape Horn and also along the west coast of South America. Now, if we look to the top right, which is the 1930s, now the big thing which has changed here is that the Panama Canal exists. So that means on the one hand, you have new shipping routes operating across the tropical Pacific from the Panama Canal to Australia and New Zealand. But on the other hand, you lose most of that west coast of the Americas traffic because ship traffic from the west coast of North America no longer has to go around Cape Horn. So the effect of that is that we have much better coverage in the eastern tropical Pacific in the 1930s than the 1890s, but we have worse coverage in the southeast Pacific. And then it progressively improves over time. But it's really not until the 1980s we get much consistent coverage in the Southern Ocean, and most of what we do get is was in the summer, not much winter data. So there certainly are coverage issues over time, but on the other hand, they have improved. Over land, there are also significant issues with data coverage in some parts of the world, both with the observations themselves and also the reliability of their reporting. So, polar regions, as you might expect, don't have much data, but there are parts, particularly Africa and South America, there are parts which either don't have much data or don't report very reliably. Unreliable reporting can also be a problem in the Pacific, and there is quite a bit of work going on at World Meteorological Organisation level to try and address some of those reporting issues, but that doesn't address the issue of some areas not having observations in the first place. So that leads me on to the question of how data is distributed and archived. And meteorology has long had a very strong international element. It's been recognised since the earliest of days that the atmosphere doesn't recognise national borders. So to be able to do any sort of serious meteorological work, initially weather forecasting and later climate, having some sort of system for international data exchange was critical. And in fact, began originally in the early 19th century in Europe under the auspices of some private scientific societies. But by 1873, an organisation called the International Meteorological Organisation had been set up. which was a non-governmental organisation but provided a forum for developing standards and data exchange. By 1873, you were also starting to get national meteorological services develop. The first of them was the British Meteorological Office, which I think was about 1854, and more after that. And then after the Second World War, with the establishment of the United Nations, the World Meteorological Organisation was established as a UN agency, which was a governmental agency, and its members are formally the National Meteorological Services or equivalent. Now, there are a lot of things that WMO does, but one of the specific things it does is it has a system for exchanging data between countries, using a whole sequence of codes for distributing messages. A lot of those are real-time observations, which are designed for weather forecasting, but for climate data, the main channel that we have is what's referred to as the ClearMap message, which is a monthly message which gives the monthly averages or totals for a range of elements such as maximum minimum temperature, rainfall, air pressure, and so on. And those data, because they're a few days after the end of the month, usually have at least some level of quality control at national level, whereas the real-time hourly and daily data don't. Now, WMO doesn't do its own data archiving, but there are a number of other institutions that do. One major one there is the National Centre for Environmental Information in the US, which falls under the parent department that's responsible for meteorology in the US government. There are other specialist centres as well. There's one that manages ocean data. The German Weather Service has a global archive of rainfall and snowfall data. So there are a number of global data archives, and those are really important for analysis. Now, one particular issue we have, especially at shorter timescales, is that a lot of historical data still exists only on paper. In the case of Australia, that incorporates a lot of daily and sub-daily data before 1957. After 1957, most things went onto computer, but before 1957, a lot of stuff has, most of the monthly data is available digitally and most of the daily rainfall data is available digitally, but a lot of other elements aren't. So to be able to do anything, with this, you need to find the physical documents, and that's sometimes not trivial. And I mentioned, for example, the Adelaide parallel observations before. A lot of the data we found for that by accident when somebody found it in a box when the Adelaide Office of the Bureau was moving about 10 years ago. So you need to find the physical documents, and then need to image them and enter the data into databases. And that's often a very labour-intensive process, particularly because, at least to date, optical character recognition generally doesn't work well with numerical data, because one of the things that OCR depends on is when it's just scanning words, is using the surrounding letters to provide context to the letter it's providing. But in numerical data, one digit will usually not tell you anything about what to expect with the digits before or after. One interesting angle which has been carried out in some countries is to do this through citizen science projects, where images are displayed online and volunteers are asked to digitise them. There was one spectacular success here with British rainfall records, which a project was being set up around the start of 2020 to digitise a lot of the historical British rainfall records, and all of the images have been put online, and they put out a call for volunteers, and they're expecting to take years to get it finished. Of course, very slightly later in 2020, you had a awful lot of people sitting at home with not very much to do, and quite a lot of them got interested in transcribing rainfall data. And the upshot of this was that the project they were expecting to take years to finish got done in a few weeks. So I guess that was one positive spin-off of all the events of 2020 and 2021. Uh, So even once you've got the digital data, creating global databases is pretty hard because the historical data is primarily at national level, and there isn't currently any standard mechanism yet in WMO for exchanging historical data. So it means that data centres have to make contact, at least for historical data, with a lot of individual countries to try to get information. Now, sometimes even if the data exists, there can be data policy issues. Some countries have open data policies and are very willing to provide data. Others will provide data to international data centres, but on the condition that it's not redistributed. So, for example, I mentioned earlier the German weather service has a global precipitation database, but the products they make available are spatially interpolated gridded products, not the input station data. And some countries do have pretty restricted data policies, and that can be for a number of reasons. Sometimes it's because they see commercial value in their data. Sometimes it can be for more what are call cultural reasons. And we find, for example, that a lot of Pacific Island countries are pretty protective of data, and I think some of that is because in a lot of those societies, they're coming from a cultural background where information is something that is controlled and is available only to suitably initiated members of the community, and that attitude can spill over a bit into other types of information. But just a couple of years ago, the WMO Congress, which is all the member countries, did pass a resolution which in effect does require countries to make historical data freely available, but the implementation of that's probably going to take at least several years to play itself out. All of this affects daily and sub-daily data much more than it does monthly. So whilst there are a number of global monthly databases in existence, and that's what we use for IPCC, there isn't really a good global daily database in existence, and that makes it quite difficult to do assessments of extremes. And a final problem we have sometimes is that we get data from different sources, and that has to be reconciled. It might be that they're for different. They turn out to be for different places in the same general area. So you might get one global data set where the nominal Adelaide data is for the site in the parklands, and another one where the nominal Adelaide data is for the airport. Now, if they have good station identifiers, it should be possible to reconcile those, but not everywhere has those. So that can be a challenge as well. Now, when we analyse global data sets, temperature data sets, the standard is we're always doing them on the basis of anomalies from a standard reference period. And typically this will be something like 1961 to 1990 as a baseline. Now, main reasons for this are, firstly, that anomaly fields are much smoother and have longer length scales than raw data fields, which in turn means that you can interpolate over much longer distances, which is important in data sparse areas. But it also means that you don't get major biases arising when stations enter or leave a network. So, for example, if we look at if we look at, say, Australia, a lot of the stations in the more remote parts of the country have, opened more recently than the stations in the south and around the coast. So if you just did an average of temperatures from all stations in Australia that report, you'd get artificial warming over time as more and more of the stations came from hotter parts of the country. But using an anomaly-based analysis does get around most of that problem. It doesn't completely avoid it, but as I'll explain a little bit later on. Uh, and in fact, one of the major issues here is that we know that the Arctic is the world's fastest warming region, and it's warming in recent decades at 2 to 3 times the global average. But most of the Arctic has very limited data. Now, what that means is that if the way your data set is analysed treats areas with little data as missing, they will tend to undersample the Arctic. They'll undersample the Antarctic as well, but that's not so much of an issue from a bias perspective. And a data set which undersamples the Arctic is going to underestimate the amount of global warming. Now, when we look at the different data sets that are produced internationally, and there are a number of different data sets produced by different institutions. So I've got 4 examples here. The top left one is from the British Meteorological Office. Bottom left one is from National Centre for Environmental Information in the US, which I mentioned earlier. Top right is NASA, and the bottom right is one which is done by a private group out of Berkeley in the US. Now, these all have somewhat different source status. They use different methods for data homogenisation. Some of them do a lot of their own. Some of them are drawing to a large extent on input national data sets. And they use different methods for interpolating data, but they're not completely independent. So, some of these data sets use the same sea surface temperature analysis essentially, but are different on land or vice versa. We also have a different type of data set which we call reanalysis. And what this is actually effectively rerunning a weather forecast model, and all the data that gets assimilated into the model to assess the current state of the atmosphere. Now, these have the advantage that they can assimilate a very wide range of data types, and they have full global coverage, and they're available quite quickly. The data sets I showed earlier are typically only available 2 to 3 weeks after the end of the month because it takes that long for the source data to arrive, whereas the reanalyses, because they're drawing on the real-time data, are typically available on a lag of only a few days. And if you're hearing reports about such and such a day being the world's hottest day on record, that will be coming from a reanalysis. But for longer-term climate change analyses, they become more problematic. We've found that what we call ERA 5, which is a European product, is pretty good for temperatures after about 1980, but less good before then, partly because of changes in the input data, and they stop altogether. I think they go back to 1940. So if you're looking for changes since pre-industrial, you can't really use them, but as an indicator of current conditions, they're very useful. So at the end of all of this, what determined what went into the IPCC analysis, which I'm really showing on the right. So our criteria here were that obvious starting point was we had data back to 1850. We wanted a data set that was what we referred to as globally complete, so fully interpolated, so that including full sampling of the Arctic. A lot of the latest generation of sea surface temperature analyses, including adjusting for transition from ship to buoy measurements. And, somewhat arcane point is that over areas of sea ice, there were some data sets that didn't attempt to estimate temperatures over sea ice and just used long-term averages, so we excluded those. And at the end of the day, there were 4 data sets in production which fully met those conditions, and there was a 5th that met all the criteria except for sea ice, so we used that in the land assessment but not the ocean assessment. Now, the spread between the data sets was part of what went into the uncertainty assessment we made in the IPCC numbers. Now, a final point is, how do we assess how much temperature has changed? And I, mentioned earlier on that our primary metric in IPCC was the change between the average of the 1850 to 1900 period and the most recent decade. That's actually a change in practice from previous reports. In previous reports, we used a linear trend as a primary metric, but it was clear that with global warming trends, the linear trend was becoming a less good representation of what was going on. And, almost all years in the last 20 years are well above the linear trend. So a linear trend would tend to underestimate the level of warming. Also show here the global temperature time series that were used in the 2021 report and also the 2013 report. And the 2021 data series does show a bit more warming, and that's largely about accounting for those two issues I talked about before, the transition to buoys and sea surface temperatures, and also better coverage in polar regions. Now, finally, a few, some matters relating to the definitions and what things mean. So I mentioned earlier that the Paris Agreement means countries commit to keeping warming as close as possible to 1.5 degrees above pre-industrial levels. Of course, in the best traditions of diplomacy, the agreement doesn't actually define what pre-industrial is or how warming levels are measured. So that was left to be IPCC's job. And as I mentioned earlier, for observed temperatures, we use 1850 to 1900 as an approximation. There is quite a lot of indirect evidence that indicates that that 1850 to 1900 period is actually very close to a true pre-industrial. So that's encouraging in that sense. IPCC has also defined warming levels as based on the midpoint of a 20-year average. So what that means is that a single year above 1.5 degrees doesn't mean that we've reached the Paris Agreement thresholds, although when it happens, everybody will no doubt think it has. We have actually already had individual months above 1.5 degrees, both in the last year and going back a bit further at the peak of the 2015-16 El Nino as well. And finally, how do we keep track of where warming is now? So an average for the last decade is obviously a lagging indicator. Effectively, it's a lagging indicator by 5 to 6 years. And with warming currently occurring at a rate of 0.2 to 0.25 degrees per decade, that means that just taking a decadal average will understate the current state of warming. Now, the IPCC definition of long-term warming is useful, but because it's based on the midpoint of a 20-year period, at any given point in time, you don't know what's going to happen in the last 9 years of that period. So effectively, to be able to assess estimated warming levels under the IPCC definition, you need to make an estimate of what temperatures will be in the next 9 years. Been a couple of methods used to do that. One which I developed was looking at the historical statistical relationships between temperatures early and late in a 20-year period. And another method, which was led by the UK Met Office, is based on short-range climate model projections. And both of those actually come out with pretty similar answers for where we are now, which is encouraging, which is in the mid-1.2s. And finally, 2023 was an exceptional year. It was clearly the warmest year on record in all data sets, exactly where it was, depending on which specific data set you have. Now, one of the interesting things about this is that, it is normal for global temperatures to be above trend during El Nino years. But the strongest signal in global temperatures is normally in the second year of an El Nino. So in the context of present, what that would mean is we expected to see a very warm year in 2024. We were a bit more surprised to see a very warm year in 2023. You can get extremely warm years without an El Nino, but it's much less common. And 2023, in terms of how far the year was above long-term trends, is probably close to the most exceptionally warm individual year in the last century. So, and there's, as you can imagine, it's a very active area of research trying to determine what the drivers of that were. Was it El Nino acting in an unusual way? Are there other contributors? There's, been some work being done on things like reduced sulphur emissions from ships possibly having an influence, potentially, water vapour in the upper atmosphere injected by the big volcano that blew its top near Tonga a couple of years ago. But that's all a very active area of research. But it'll be interesting to see how 2024 comes in. At the moment, 2024 is probably on track to have a fairly similar number to 2023, but that's assuming that we get the usual cooling we get in the second half of the year when an El Nino ends. It remains to be seen whether that will happen. That takes me to the end of the presentation, so I guess we open things up for questions.
Thank you, Blair. That talk was both fascinating and alarming. If anyone's got a question, please either put it in the chat or you can just simply unmute yourself and ask the question. I'll start out with asking, I didn't realise there were so many factors into the measurement era. I know in Adelaide we moved our observatory in 1977 over to Kent Town, and then they decided to move it back. And then I think they had a few years of dual measurements. Is that what you meant by the pairing algorithm?
Yeah. Well, okay. So there's a couple of different types of cases. So in some cases, when you've got a site move or other significant change, there will be a period of parallel observations between the two sites. And in the case of the Adelaide move, that happened at both ends of the change. So the original shift to Kent Town, there are parallel observations between 1977 and 79, and with the move back, there were parallel observations between 2017 and 2020, and that's definitely considered to be best practice. If you are planning a move, and it would be for a planned move. It's now, for example, standard bureau policy that we undertake at least 2 years of parallel observations if at all possible. But obviously that hasn't been the case, for many changes historically, and it also won't help you if you have changes happening in situ, such as a change in local site environment. In those cases, what we do is we compare the data at the target station with data with the best correlated other stations in the region. So, if you were trying to assess it, a change at Adelaide, which you didn't have parallel observations for, you might do comparisons with places like Parafield and Edinburgh, and Lunga and Roseworthy, and a few other places around. But obviously, with that process, there's a higher level of uncertainty in the adjustment compared to what you would get if you had parallel observations.
I'm sure quite a lot of variability even within Adelaide.
Yeah, and one of the interesting things here is that, which I didn't really touch on in the talk, is that some changes will have different effects in different seasons, and some will have different effects in different types of weather conditions. In particular, I talked a little bit about topographic influences on temperature, and those tend to be greatest on cold nights. So you'll often find that something like a site move will affect extreme minimum temperatures more than it affects averages. And the method that we use for the adjustments in Australia accounts for that. You also get some interesting seasonal effects going on, and one I think one nice example we had was at Snowtown, where the site moved from the post office to a wheat cropping area a couple of k's out of town in the 1990s. And what we found was that the new site is, for maximum temperatures, is colder in winter and spring when you have a lot of green vegetation around, but it's hotter in summer than the town when the ground's generally pretty bare. One interesting aspect of that is that it was trying to, I suspected that was what was going on, was trying to confirm that. And all our site photos on our files were from summer and autumn, so I didn't actually have any site photos from winter or spring. So I got a friend of mine, a friend Florence as well, who's a truck driver who works in South Australia, to take some photos for next time he was going past.
Does anyone else have any questions? Because otherwise, I've actually got one more. You talked about how you're no longer using linear trends.
Yeah.
Could you explain a little bit more about what are you assuming a functional form, say like an exponential, or you said something about
No,
differences?
the primary metric we're using is simply the difference between the means of the baseline period and the most recent decade. We have found that the decadal mean actually doesn't have that much internal variability, probably because a decade's long enough to sample all of the El Nino La Nina cycle, which is the main driver of internal variability in global temperatures. There was some work done with the Australian data set, which looked at fitting various functions to the time series, and found that at least at the time, that didn't make all that much difference to the total assessed change. That is not guaranteed to be the case into the future, and I suspect you probably get different results if you applied it for global data as well.
Okay, thanks, Blair. Does anyone else have any questions? So just one last question. I probably shouldn't ask this, where do you think we'll be in 20 years? Will humans have finally stepped up and done something well globally about climate change?
Yeah, well, that's I guess that's the big question. But I think one thing to bear in mind here is that whatever happens to greenhouse gas emissions, the time lag between a change in emissions pathway and the resultant impact of that change on the temperature is about 15 to 20 years, and that's largely because it takes that long for the deep ocean to catch up to the energy imbalance in the atmosphere. So what that means is that the warming we'll see over the next 15 to 20 years is largely determined by the emissions that have already happened, and there's basically nothing we can do about that. What the difference that future emissions will make is that what happens after that. And in essence, other parts of the IPCC report found essentially that, firstly, that stabilisation of global temperatures at any level requires reaching net zero emissions, and secondly, that the level that stabilisation happens at is largely determined by the total quantity of emissions before you reach net zero.
Well, the future's in our hands. Thank
Yeah.
you, Blair, once again for stepping in and speaking to us here on a topic that affects all of us.